Little red dots, the impossible black holes at the dawn of time. There is a kind of light that should not exist. It is older than the sun, the earth, nearly everything we call ancient. When the James Webb Space Telescope turned toward the deepest dark it could find, it caught tiny points of red shining from an age when the universe was barely a toddler, less than 1.5 billion years old. Astronomers named them the little red dots. Inside, many sit black holes so massive, so early, that the timeline of the cosmos seems to break. Stay with me, like and subscribe so this story reaches more curious minds. And tell me in the comments where you are watching from and what time it is. Let us begin with something you already know, or at least something you have been taught to believe. The universe is patient. That is the story most of us carry quietly in the back of the mind, the gentle assumption that everything grand was built slowly. Mountains rise grain by grain, canyons are carved river by river over millions of years. And the cosmos, we are told, works the same way, only stretched across a scale of time so vast that our small lives barely register against it. Galaxies took ages to assemble. Stars lit one after another like candles in a slowly waking city. And the great black holes, the monsters that sit at the hearts of galaxies, grew the way a tree grows, ring upon ring, eon upon eon. It is a comforting picture. It is also the picture that science itself painted for most of the last century. So if you carry that belief, you are in excellent company. The brightest minds in cosmology carried it too. And that is exactly why what happened next matters so much. Picture the early universe the way the textbooks describe it. In the beginning there is heat and light, and a fog so thick that light itself cannot travel freely. For hundreds of thousands of years, the cosmos is an opaque sea of particles. Then it cools, and the fog clears, and for a long stretch there is darkness. No stars yet, no galaxies, just hydrogen and helium drifting in the dark, waiting. Astronomers call this the cosmic dark ages, and the name fits. Nothing shines. The universe is holding its breath. Slowly, gravity does its quiet work. The faint clumps in that drifting gas pull on one another. Matter gathers. The first stars ignite, enormous and short-lived, blazing and then dying in violent collapse. From their deaths come the first seeds of black holes, modest things at first, a few tens of times the mass of our Sunday around them. Gas continues to fall inward, and galaxies begin to take shape. The black holes feed on what falls near them. They grow. The galaxies grow with them. And across billions of years, this dance builds the universe we recognize. A universe of spiral arms and bright cores and titanic black holes, weighing millions or billions of times the mass of the Sunday. The key word in all of that is slowly. Every step takes time. A black hole cannot simply swallow the universe in an afternoon. There are limits, physical rules that govern how fast it can eat. We will return to those rules later, because they sit at the very center of this mystery. For now, hold on to the feeling of order, seed, then growth, then maturity. Small things become big things, and bigness is the reward of age. The biggest black holes should be the oldest ones, and the oldest ones should live in a universe that has had plenty of time to make them. This was not just a vague intuition. It was woven into the mathematics of how we model the cosmos. It shaped what astronomers expected to see when they looked back in time. And here is the wonderful, strange truth about astronomy. When you look far enough across space, you are also looking back across time. Light is fast, but it is not infinitely fast. The light reaching your eye from the sun left it about 8 minutes ago. The light from distant stars has traveled for years, for centuries, for thousands of years. And the light from the most distant galaxies has been traveling for almost the entire age of the universe. To look deep into space is to look into the deep past. A powerful enough telescope is not just a camera, it is a time machine. For decades, our finest time machine was the Hubble Space Telescope. It gave us images that rewired the human imagination. In one famous experiment, astronomers pointed Hubble at a patch of sky that looked utterly empty, a speck so small you could cover it with a grain of sand held at arm's length. They left the shutter open and gathered light for days. And out of that apparent nothing emerged thousands of galaxies, each one a city of stars, scattered back through time. It was one of the most humbling images ever made. The lesson seemed clear. The deeper we look, the more we find, and the younger and smaller and simpler those distant galaxies appear, exactly as the patient story predicted. So the stage was set. We had a theory that felt solid. We had observations that seemed to confirm it. The early universe, in our minds, was a place of modest beginnings, of small galaxies and small young black holes just starting their long climb toward maturity. Everyone expected the next great telescope to fill in the gentle details of that climb, to show us the cosmos taking its first careful steps. And then we built a better time machine. The James Webb Space Telescope is not simply a bigger Hubble. It is a different kind of eye entirely. Hubble sees mostly the light our own eyes can see, with a little ultraviolet on one side and a little infrared on the other. Webb is built to see infrared, the long, warm wavelengths that lie just beyond the red edge of human vision. This choice is not an accident. It is the whole point. Because the universe is expanding, the light from the most distant objects gets stretched as it travels. Light that began its journey as ordinary visible light, or even as ultraviolet, arrives at us stretched far into the infrared. To see the first galaxies, you must see in infrared. You must build an eye for the kind of light that the dawn of time has become by the moment it reaches us. So Webb was sent 1,000,000 miles from Earth, far beyond the moon, to a quiet point in space where it could sit in the cold and the dark and stare without interruption. Its great golden mirror unfolded like a flower. Its sunshield, the size of a tennis court, spread out to block the heat of the sun and the earth and the moon, so that the faint warmth of the early universe would not be drowned out. And then, in the summer of the year 2022, it opened its eye. The first images were breathtaking in the ordinary sense, beautiful and sharp and deep. But for the astronomers studying the most distant objects, beauty quickly gave way to something else, to unease. Because the deep fields that Webb returned were not quite behaving. Remember the patient story. In the first billion years or so after the beginning, the universe should hold small things, faint, young, modest galaxies, just beginning to grow. That is what the models predicted. That is what the careful arithmetic of cosmic growth required. So when astronomers began counting what Webb found in those early epochs, They expected a certain number of objects of a certain brightness, and they expected those numbers to be small. The numbers were not small. There were too many bright things too early. Galaxies that looked too grown up for their age. Objects glowing with more light than they had any right to possess so soon after the beginning. At first, this was met with the proper caution of science. Perhaps the distances were wrong. Perhaps these bright specks were nearer than they seemed, ordinary galaxies masquerading as ancient ones. Distance in astronomy is a subtle and tricky thing, and the history of the field is full of cautionary tales about jumping to conclusions. So the community did what good scientists do. It doubted. It checked. It demanded better evidence. And then, scattered through those deep fields, a particular kind of object began to catch attention. Not the brightest things, and not the most obvious. Something quieter and stranger. Tiny points of light, so compact they looked almost like single stars rather than galaxies. And they were red. Not warmly red, not the soft red of a sunset, but deeply, unusually red, as if something had taken ordinary light and steeped it in something dark. Here and there, then, everywhere astronomers looked, these little crimson points kept turning up. At first they were a curiosity, a footnote, the kind of thing you note and set aside, planning to understand later. But the footnote would not stay quiet. The more carefully astronomers searched the early universe, the more of these red specks they found. They were not rare. They were not freaks. They were a population, a whole class of objects that the patient story had never predicted and could not easily explain. Someone, looking at how they appeared on the screen, gave them a plain and honest name, the little red dots. And in that plainness there is something worth pausing on. So often in science, the impulse is to wrap a mystery in grand or vague language, to call something enigmatic or mysterious and leave it there, as if naming the confusion were the same as facing it. The little red dots got a name that simply describes what you see. Little red dots. The name does not pretend to know what they are, but it does not hide from them either. It points straight at the strange thing in the data and says, "Here, look at this. We do not understand it yet." Hold that name in your mind, because we are going to spend the rest of this journey trying to understand what hides inside it. And I want to be honest with you from the start. We will not arrive at a tidy ending. There is no neat box to close at the finish. What we have instead is something rarer, and I think more thrilling. We have a genuine open question at the frontier of human knowledge, the kind of question that working scientists are arguing about right now in this very year, with new data arriving faster than the theories can keep up. But before we open the dots and look inside, sit for a moment longer with where we are, because the emotional truth of this story is not really about telescopes or wavelengths or numbers. It is about a quiet shock that ran through a field of careful, brilliant people. For a century they had built a picture of how the universe grew, a picture of patience and slow accumulation, and they had every reason to trust it. The mathematics was elegant, the earlier observations fit. The story made sense. And then a new eye opened on the sky, looked back toward the beginning of everything, and found something the story did not allow. That is the feeling I want you to hold as we go deeper. Not the smug pleasure of being told someone else was wrong, but the vertigo of realizing that the ground you were standing on might be thinner than you thought. Every one of us walks around with a model of how the world works, a quiet set of assumptions we rarely examine. Most of the time, those assumptions serve us well. And then, every so often, reality sends back a signal that does not fit, a little red dot in the data of our lives, and we are faced with a choice. We can look away and protect the comfortable story, or we can lean in, unsettled and curious, and let the strangeness teach us something. The astronomers chose to lean in. They turned the full power of their instruments toward those tiny red points. They gathered their light not just as images but as spectra, splitting it apart into its component colors, the way a prism splits sunlight into a rainbow. Because hidden in those colors is a wealth of information that a simple picture can never reveal. They wanted to know how far away the dots truly were. They wanted to know what they were made of. They wanted to know, most of all, whether these were ordinary objects wearing a strange disguise, or whether they were something the universe was not supposed to contain so early. What they found in that split light did not calm the unease. It deepened it into something close to disbelief, because when they pulled apart the color of a little red dot and read the story written there, they saw the unmistakable fingerprint of gas moving at tremendous speed, swirling around something enormous and unseen. They saw the signature of a black hole, and not a modest young seed of a black hole, the kind the patient story would permit. They saw evidence of giants, monsters, black holes that, by every rule we thought we understood, simply did not have time to exist. Let me slow down here, because it is worth understanding just how deeply the patient story was woven into everything, so that you can feel the size of what was about to crack. The slow growth picture was not a single idea you could remove like one brick from a wall. It was the mortar holding the whole wall together. It shaped how we estimated the ages of galaxies. It shaped how we modeled the way matter clumped together under gravity across cosmic history. It shaped the great computer simulations, the vast digital universes that astronomers grow inside their machines. Feeding in the laws of physics at the beginning and watching galaxies and black holes assemble over simulated eons. Those simulations were triumphs. They reproduced the cosmic web of galaxies we actually observe, the filaments and voids, the great clusters strung like beads along invisible threads of gravity. When your model can grow a universe that looks like the real one, you trust it, you build on it. You let it tell you what to expect when you look somewhere new. And what the simulations expected in the first billion years was modesty. Small, dark clumps of matter gathering their first stars. Little galaxies flickering on, faint and ragged, slowly merging and growing. Black holes still in their infancy, feeding gently, nowhere near their eventual size. This was not a guess pulled from the air. It was the considered output of our very best understanding, refined over decades, checked against everything Hubble and its companions had shown us. The early universe, the models insisted, should be a place of small beginnings. There is a human tendency worth naming here, because it runs through the whole history of science. When a theory works well for a long time, we begin to mistake it for reality itself rather than a map of reality. The map had served us so faithfully that we half forgot it was a map. We forgot that it described only the territory we had already explored, and that the deepest, earliest reaches of cosmic time remained almost entirely uncharted, hidden behind a veil of distance and faintness that no telescope had yet pierced. The patient's story felt less like a theory and more like common sense. And common sense, in physics, is exactly the thing the universe most enjoys overturning. Consider how often this has happened before. Common sense once said the earth sat fixed at the center of all things. Common sense once said the universe was eternal and unchanging. Common sense once said our galaxy was the whole of creation, until we learned that those faint smudges in the sky were other galaxies, island universes drifting at distances the mind can barely hold. Every one of those overturnings felt, beforehand, impossible, and afterward, obvious. The history of astronomy is in large part the history of comfortable certainties dissolving when a sharper instrument arrived. So perhaps we should have been ready. Perhaps we should have suspected that a telescope built specifically to see further back than ever before would not simply confirm what we already believed. New eyes do not usually flatter old stories, but knowing this in principle and feeling it in the data are two very different things. The astronomers who first counted the early objects in Webb fields were not looking to overturn anything. They were doing careful, ordinary work, the patient tallying that science is mostly made of. They expected the numbers to land where the models said, and when the numbers refused, the first response was not excitement, it was worry. The quiet professional dread that creeps in when your instrument shows you something it should not. Did we make an error? Is the calibration off? Are we fooling ourselves? That dread is the proper companion of every real discovery, because the line between a revolution and a mistake is thin, and only relentless checking can tell them apart. So they checked, and checked again, and the strangeness held. The early universe was brighter and busier and more grown up than the patient's story allowed. And in the middle of that broad, unsettling abundance sat the little red dots, quiet and specific and impossible to dismiss, a tightly defined puzzle within the larger one. They were not just more of the general strangeness. They were a particular kind of strangeness, a population with a consistent character, almost as if the universe had left the same odd signature in the same hand again and again across the early sky. A repeated pattern is far harder to wave away than a single oddity. A repeated pattern means something is happening, something systematic, something the story has no room for. That is where we are headed. But to understand why a single fingerprint in stretched red light could shake the foundations of cosmology, you first need to understand what these little red dots really are, how we measure the staggering distances involved, and what it truly means to say that an object comes to us from the dawn of time. So let us leave the comfort of the patient story behind for good, and step closer to the dots themselves. So, what exactly is a little red dot? Let us build the answer slowly, the way the astronomers had to, one clue at a time. Start with the most obvious feature, the one that gave them their name. They are small. When Webb captures a distant galaxy, you can usually see that it has some shape, some extent, a smear of light with structure inside it, the way a city seen from an airplane resolves into streets and districts. The little red dots refuse to do this. No matter how sharp the telescope, they remain points, unresolved, a single concentrated spark of light with no visible body around it. In the language of astronomy, they look like point sources, the same way a star looks like a point even through a great telescope. because it is so far away that all its light arrives from what is effectively a single direction. For a galaxy to look that compact across such an enormous distance, whatever is producing the light must be packed into a tiny region. Something is crammed into a space far smaller than a normal galaxy. Now add the color. This is where the second half of the name comes from, and it is stranger than it first appears. The little red dots are not simply red. They have a peculiar split personality in their light. In the ultraviolet, the short high-energy end of the spectrum, they tend to look faintly blue. But in the optical, the part of the spectrum nearer to what our eyes can see, they turn sharply, deeply red. Imagine a face that is pale on one side and flushed crimson on the other. That is the shape of their light, a kind of V or hook when you plot brightness against color, blue rising on one side and red rising on the other. This double nature is a clue, and a confusing one, because the two halves seem to tell different stories. We will come back to what could possibly produce such a shape, because it sits at the heart of the debate over their nature. But the feature that truly sets the field on fire is not the size or the color on its own. It is how many of them there are. And to feel the weight of that, you need to understand what these objects are not. They are not nearby. They are not local oddities sitting in our cosmic neighborhood. They come to us from staggeringly far away, and therefore from staggeringly long ago. To explain how we know that, I need to tell you about one of the most beautiful and reliable tools in all of astronomy, redshift. Light is a wave. Different colors are simply different wavelengths, different distances between the crests of that wave. Blue light has short wavelengths packed tightly together. Red light has longer wavelengths spread further apart. Now here is the crucial fact about our universe. It is expanding. Not expanding into anything, and not with the galaxies flying through space like shrapnel, but the very fabric of space itself stretching, swelling, growing between things over time. And as light travels across that swelling space, the light stretches with it. A wave that set out blue arrives a little redder. A wave that traveled for a very long time across a great deal of expanding space arrives much redder than it began. The longer the journey, the greater the stretch. This stretching is what we call redshift. This is not guesswork. Atoms emit and absorb light at very precise, very specific wavelengths, like a barcode unique to each element. Hydrogen has its barcode, helium has its own. Oxygen, carbon, iron, each leaves a distinctive pattern of bright or dark lines in the spectrum of light. When astronomers split the light of a distant object and find that familiar barcode shifted, every line moved together toward the red by exactly the same proportion, they can measure precisely how much the light has stretched. And from that stretch, they can calculate how long the light has been traveling, and therefore how far away the object is and how far back in time we are seeing it. Astronomers measure this stretch with a number they call z. A small z means a small stretch and a nearby, recent object. A large z means an enormous stretch and an ancient, distant one. The little red dots that have caused all the trouble cluster at redshifts of roughly 5 to 9. Let me translate what that range of numbers actually means, because the bare figures hide the astonishment. A redshift of around 5 means we are seeing light that left its source when the universe was roughly 1 billion years old. A redshift of around 9 pushes that back to when the cosmos had existed for only about 500 million years. Set against the present age of the universe, which is close to 14 billion years, these objects come from the first 8 or 9% of all cosmic time. If you compress the entire history of the universe into a single year, with the beginning on the 1st of January and this present moment at midnight on the 31st of December, then the little red dots are shining at us from somewhere in the first few weeks of January. They are not from the childhood of the universe. They are from its infancy. The light entering Webb tonight set out before the earth existed, before the sun existed, before most of the atoms in your body had been forged in the hearts of stars that had not yet been born. Sit with that for a moment. The photons that paint these little red dots onto our detectors have been falling through expanding space for more than 13 billion years. They crossed an unimaginable gulf, stretched and reddened the whole way, and at the end of that journey they were caught by a golden mirror unfolded by human hands in the cold beyond the moon. We did not just find these objects. We reached back across almost the entire age of existence and held their light in our instruments. That alone should stop you in your tracks. Now bring back the question of number, because this is where the patient story first cracks open. When astronomers tally how many little red dots appear in the early universe, the count comes out far higher than anyone expected. These are not 1 in a million flukes. In some of the deep surveys, a meaningful fraction of all the compact red sources at these early epochs turn out to be little red dots. They are common, and common is a devastating word here, because the patient story did not merely fail to predict a few of these objects. It failed to predict an entire abundant population of them, a population that seems to switch on early in cosmic history and then fade away, far more numerous in that first stretch of time than at any later age. Whatever the dots are, they represent something the early universe did frequently and the later universe stopped doing. That is a profound clue and a profound problem. You might reasonably ask whether astronomers could be fooling themselves. Could these red points be something ordinary in disguise? This is the right question, and the community asked it relentlessly. Perhaps they are cool red stars in our own galaxy, nearby and faint, only pretending to be distant. Perhaps they are dusty galaxies whose redness comes from grime rather than great distance. Perhaps the whole thing is a trick of measurement, a bias in how the surveys were built. Every one of these alternatives was taken seriously, because extraordinary claims demand the killing of ordinary explanations first. And one by one, for a large and growing sample of these objects, the ordinary explanations were tested and found wanting. The redshifts held up. The distances were real. The little red dots truly are messengers from the dawn of time, and there are far more of them than there should be. But the count, as shocking as it was, only told astronomers how many and how far. It did not tell them what the dots are. To answer that, they needed to do for the little red dots what we do for any mysterious light in the sky. They needed to read its spectrum in detail. Not just measure the overall color, blue here and red there, but split the light finely enough to see the individual barcode lines of the elements within, and to study the exact shape of those lines. Because the shape of a spectral line is not just a marker of which element is present, it is a recording of motion. It is, in a very real sense, the fingerprint of how the gas producing that light is moving. And here we arrive. At the moment, the mystery turned from strange to staggering. When astronomers took the highest quality spectra of little red dots, gathering their faint stretched light for hours, and pulled it apart into its finest detail, they found emission lines, bright spikes in the spectrum where atoms, mostly hydrogen, were pouring out light at their characteristic wavelengths. That in itself was expected. Hot gas glows, and glowing hydrogen is the most ordinary thing in the cosmos. But it was not the presence of the lines that stunned them, it was the width. A spectral line from gas that is sitting still or drifting gently is narrow. A thin, sharp spike at a precise wavelength. But a spectral line from gas that is moving violently, some of it rushing toward us and some of it rushing away at the same instant, gets smeared out. The light from the gas coming toward us is shifted slightly blue. The light from the gas racing away is shifted slightly red. And when you add it all together, the once thin spike spreads into a broad, swollen hump. The faster the gas is moving, the broader the line. A broad emission line is the unmistakable signature of gas whipping around at tremendous speed. The little red dots showed broad lines, very broad. The kind of breadth that implies gas moving at thousands of kilometers every second, hurtling around in tight, furious orbits. And in the universe, there is only a short list of things that can fling gas around that fast in such a confined space. At the top of that list, casting its long shadow over everything that follows, is a black hole. Not a stellar corpse, a few times the mass of the sun, but something far heavier, something with enough gravity to seize gas and swing it around at a meaningful fraction of the speed of light. So picture the situation the astronomers now faced. They had a tiny point of light, far too compact to be an ordinary galaxy. It came from the first billion years of cosmic time, when the universe was supposed to hold only modest young things. There were far more of these objects than any model allowed, and buried in their light was the screaming signature of gas orbiting something immense and invisible at terrifying speed. The pieces did not fit the patient's story. They did not fit it at all. Let me linger on the spectrum a little longer, because the spectrum is the secret heart of this entire field, and most people never get told how much it can reveal. When you look at a star or a galaxy with your eye, or even in a sharp photograph, you receive almost no information about what it is made of or how it moves. You get a smear of color and a brightness, and that is all. But split that light through a prism or its modern equivalent, spread it out into its full rainbow, and the smear blossoms into a rich and readable text. Every element writes itself into that rainbow in a unique pattern of bright and dark lines. The presence of hydrogen, the trace of helium, the signature of oxygen or carbon or iron, each announces itself at precise wavelengths. From the spectrum alone, without ever touching an object trillions of miles away, we can know its chemistry, we can know its temperature, we can know how fast it is approaching or receding. And from the exact shape of each line, we can know how the gas producing it is churning and swirling. The spectrum is a confession. It is the universe telling you, in a language we have learned to read, what it is and what it is doing. This is why the spectra of the little red dots mattered so much more than the images. An image told us they were small and red. A spectrum could tell us what they truly were, and gathering those spectra was no small feat. These objects are faint, their light stretched and dimmed by its long journey, and to split that already feeble light into a detailed rainbow, you must throw away most of it, spreading the few precious photons across many channels. It means staring at a single tiny target for hours, sometimes piecing together the light from many separate observations, coaxing a usable signal out of the dark. This is the unglamorous reality behind the headlines. Behind every startling result sits a mountain of patient labor, of careful instrument work, of light gathered photon by photon from the edge of time. The little red dots gave up their secrets only because people were willing to point the most expensive eye ever built at faint specks and wait. And when the spectra finally came, the first thing they confirmed was the distance. The barcode of hydrogen and other elements appeared. Every line shifted toward the red by the same proportion, locking the redshift down with a precision that imaging alone could never reach. The dots were real travelers from the deep past, beyond reasonable doubt. That alone was a triumph. But it was the second thing the spectra revealed, riding on top of the confirmed distance, that turned triumph into bewilderment. Because once you knew exactly how far the light had come, you could read the shape of the emission lines for what they truly were, and that shape spoke of violence, of speed, of gas flung around at velocities that demanded an explanation no gentle young galaxy could provide. A narrow line would have been reassuring. A narrow line would have said the gas inside these objects was calm, ordinary, drifting at the sedate speeds of normal star-forming regions. That would have fit a small young galaxy perfectly well. But the lines were not narrow, they bulged. They spread out into broad, swollen humps, the unmistakable mark of gas tearing around in tight orbits at speeds of thousands of kilometers every second. And the only ordinary thing in the universe that routinely flings gas around like that, in a region small enough to look like a single point of light across the entire age of the cosmos, is matter falling toward a black hole. The spectrum had handed the astronomers a confession they did not want to hear. It helps to hold the two shocks together, because each one alone would have been merely interesting, and it is their combination that is devastating. The first shock was the count, the sheer abundance of these compact red sources in an era that was supposed to be quiet. The second shock was what the spectra revealed inside them, the broad lines screaming of fast-moving gas and a hidden massive engine. Take either one by itself, and you might find a soothing explanation. An unexpected abundance of small red galaxies on its own you might chalk up to early star formation being more vigorous than expected. A handful of early massive black holes on their own you might explain with special circumstances. But put them together and the comfort drains away. You are no longer looking at a few rare giants. You are looking at a common, abundant population of compact objects, many of which appear to harbor massive black holes, all crowded into the first stretch of cosmic time. The early universe was not just busier than we thought. It was building heavy engines in bulk as a matter of routine, in plain view of the only theory we had, a theory that had no place for them. That is the shape of the problem the spectra delivered, and it is why the next question could not be avoided. And remember, this was not a single anomalous object that one team could quietly set aside while everyone waited for confirmation. The same broad lines, the same compact red glow, the same hint of a buried giant turned up again and again, in object after object, across different fields of the sky studied by different teams using different instruments. When independent groups looking at different patches of the early universe keep finding the same impossible thing, the impossible thing stops being a fluke and starts being a fact about the cosmos. There is no comfortable way to dismiss a pattern that reproduces itself everywhere you look. A single strange measurement can be an error. A strange measurement that repeats in many objects across many independent studies is the universe insisting on something. And when the universe insists, the only honest response is to listen and to ask what it is trying to tell us. There was now only one honest path forward. They had to ask how heavy the unseen thing at the center really was. They had to take that broad line, that smear of speeding gas, and turn it into a number, a mass. And when they did, the number that came back was so large, so impossible for an object this young, that it forced a reckoning with everything we thought we knew about how black holes are born and how fast they can grow. That number, and the beautiful, terrible problem it creates, is where we turn next. To understand why a single number broke the calm, you first need to understand how astronomers weigh something they cannot see, because that is the strange and wonderful trick at the center of this part of the story. Nobody has ever seen a black hole directly in the ordinary sense. A black hole emits no light of its own. It is, by definition, a region where gravity has grown so strong that not even light can escape. So how do you measure the mass of an object that is fundamentally invisible? You watch what it does to everything around it. Think of a stone tied to a string, swung in a circle above your head. The faster you swing it, the harder you have to pull on the string to keep it from flying away. Now imagine you could not see the string or your hand at all. You could only see the stone whirling. If you measured how fast it was moving and how wide its circle was, you could work backward and figure out how strong the unseen pull at the center must be. Gravity is that string. The gas swirling around a black hole is the stone, and the broad emission line, that smeared out hump in the spectrum, tells us exactly how fast the gas is whirling. This is the principle astronomers use. The width of the broad line reveals the speed of the orbiting gas. Other features of the light help them estimate how far that gas sits from the center. Put the speed and the distance together with the simple, unyielding law of gravity, and out comes the mass of the thing doing the pulling. It is a method refined over decades on the bright active galaxies of the nearby universe, and it works. It is how we have weighed countless black holes across cosmic time. So the astronomers took the broad lines of the little red dots and turned the crank. They measured the speeds, they estimated the distances, and the mass that came out the other end was enormous. For many of these objects, the numbers landed in the range of millions, and in some cases hundreds of millions, of times the mass of the Sunday. These were not baby black holes. By this reckoning, they were already supermassive, already in the heavyweight class, the same league as the giant black hole that sits at the center of our own galaxy and far beyond it. A black hole of 100 million solar masses is a serious object even in the mature universe of today. To find one already grown in the first billion years after the beginning is like walking into a nursery and finding a fully grown adult standing in the crib. The size is not impossible in itself. Giant black holes exist. The impossibility is the timing. And to feel why the timing is so devastating, we have to talk about the speed limit on how fast a black hole can eat. It seems obvious that a black hole should be able to grow as fast as it likes. It is the ultimate glutton, a bottomless gravitational well. Surely you just pour matter in and it swells without limit. But nature has installed a brake, and it is one of the most elegant pieces of physics in the whole story. When gas falls toward a black hole, it does not drop straight in. It piles up into a swirling disk, and as it spirals inward, it heats up through friction and compression until it blazes, glowing ferociously, often outshining all the stars of its host galaxy combined. This is what powers the brilliant beacons we call active galactic nuclei. The black hole is dark, but the meal is brilliant. And here is the catch. Light pushes. Radiation exerts pressure, a real outward force on matter. So the brighter the infalling gas glows, the harder its own light shoves outward against the next gas trying to fall in. Feed a black hole faster and faster, and at some point the glare of the meal becomes so intense that it blows away the very food trying to arrive. The inward pull of gravity and the outward push of light reach a standoff. This balance point defines a maximum sustainable feeding rate, and we call it the Eddington limit. It is named for the astrophysicist who first worked it out, and it acts as a natural throttle on how quickly any black hole can grow by eating gas. The Eddington limit does not forbid growth. It governs its pace. A black hole feeding right at that limit grows exponentially, doubling its mass over a characteristic stretch of time. That doubling time is set by physics and comes out to roughly a few tens of millions of years. That sounds fast, and on human terms, it is unthinkably long. But on cosmic terms, when you are trying to build a giant in the narrow window before the universe is even 1 billion years old, it is agonizingly slow, because exponential growth from a small seed still needs many doublings to reach 100 million solar masses, and every doubling costs you tens of millions of years. Let us do the arithmetic in feeling, if not in precise figures. Start with a seed black hole left behind by one of the first stars, a corpse of perhaps 100 solar masses. To climb from there to 100 million solar masses, you need to multiply your mass by a factor of 1 million. That is about 20 doublings. 20 doublings at tens of millions of years each begins to eat up most of the time available, and that is assuming the black hole feeds at the absolute maximum rate, continuously, without a single pause, from almost the first instant it is born. In reality, feeding is messy and intermittent. Gas runs out. Explosions from nearby dying stars blow the fuel away. The disk flickers and starves. To grow a supermassive black hole this early, you seem to need everything to go right all the time, with no margin for the chaos that real galaxies are full of. This is the timeline problem, and it is not new. Even before Webb, astronomers had found a handful of bright quasars, the blazing cores of feeding supermassive black holes, sitting uncomfortably early in cosmic history, and these had already raised eyebrows. How do you build 1 billion solar mass monster in under 1 billion years? It was a known puzzle, a sharp thorn in the side of our models, but it concerned only a rare few extreme objects, and there were ways to imagine special circumstances that might explain those isolated giants. The little red dots take that thorn and drive it deep. Because they are not a rare few, they are abundant. Suddenly, the early universe is not hiding 1 or 2 improbable giants in distant corners. It appears to be littered with overweight black holes, a whole common population of them, all facing the same impossible deadline. A special story you might invent to explain one freak object collapses when you need it to explain thousands. And there is a second twist that makes the problem stranger still, perhaps the strangest part of all. It is not just that these black holes are large, it is that they are too large for the galaxies they live in. In the mature universe, there is a remarkably tight relationship between the mass of a galaxy and the mass of the black hole at its center. The black hole is almost always a small fraction of the surrounding mass of stars, a fairly fixed ratio that holds across an enormous range of sizes, as if galaxy and black hole grew up together in lockstep, regulating one another. It is one of the most striking patterns in all of astronomy, a sign of some deep connection between the giant in the center and the city of stars around it. The little red dots seem to shatter that pattern. The black hole inside one of these objects can be a staggering fraction of the entire system, far heavier relative to its host than anything we see in the modern universe. The monster is enormous, and the city around it is small. It is as if the black hole arrived first and grew fast, with the galaxy lagging behind, the opposite of the comfortable picture in which galaxy and black hole rise together at a measured pace. The word astronomers use for this is overmassive. The black holes are overmassive for their hosts. And that single word carries an enormous implication. It suggests that in the early universe, black holes may not have been the passengers growing slowly alongside their galaxies. They may have been the first movers, the seeds around which everything else gathered. So now you can feel the full shape of the crisis. We have a tiny, compact source of light. It comes from the first billion years of time. There are far too many of these objects for any model to comfortably allow. Inside many of them, the light reveals gas whirling at thousands of kilometers per second around something unseen. The mass of that unseen thing, by our standard method, comes out at millions or hundreds of millions of times the sunday. The Eddington limit says such a mass should have taken longer to grow than the universe had yet existed, and the black hole is too heavy even for the small galaxy cradling it. Every individual clue is strange. Together, they form a knot that our patient story of cosmic growth simply cannot untie. When scientists face a knot like this, there are really only two broad ways out, and both are uncomfortable. The first possibility is that our measurements are misleading us. Perhaps the broad lines are not telling us what we think. Perhaps the gas is not actually orbiting that fast, and the masses we calculated are wildly too high. If that were true, the impossible giants might shrink down into something far more reasonable, and the crisis would soften. The second possibility is that the measurements are essentially correct. The black holes really are that massive, that early, and it is our theory of how black holes are born and grow that must be rebuilt from the foundations. Either way, something we held dear has to give. Either our reading of the light is wrong, or our story of the cosmos is wrong. That fork in the road is exactly where the most exciting science is happening right now. Brilliant people are arrayed on different sides of it, building rival explanations, each trying to dissolve the impossibility in its own way. Some are working to show that the masses are inflated by a subtle trick of physics nobody fully appreciated. Others are working to show that nature really can build giants this fast, through exotic doorways in the early universe that the patient story never imagined. and a few are reaching for ideas so strange that they blur the line between a star and a black hole entirely. Let me make the timeline problem vivid in a different way, because numbers can numb us, and I want you to feel it in your bones. Imagine you are told that somewhere there is a tree. An ordinary tree grows a ring a year, and the great old trees of our world, the ones that make us fall silent when we stand beneath them, have counted a few thousand rings across a few thousand years of patient growth. Now imagine you are taken to a forest that is only a few weeks old, a forest where the seeds were planted almost yesterday, and there, towering above the saplings, you find a tree so vast it would take 100 people holding hands to encircle its trunk. The saplings around it are exactly the age you expect. The giant is impossible. It has not had time to grow, and yet there it stands, casting its shadow over everything, undeniable, refusing to care about your sense of what should be possible. That is what an overmassive black hole in the early universe is, a redwood in a forest that is barely a sprout. You might reach for the obvious objection. Perhaps the black hole did not grow slowly at all. Perhaps it simply ate faster than we think, gorged itself far beyond the polite Eddington limit. And astronomers take this seriously. There are ideas about brief episodes of super Eddington feeding, where a black hole somehow swallows matter faster than the standard brake should allow, perhaps because the geometry of the infalling gas lets some of the outward light escape sideways while matter pours in along other paths. These ideas are real and actively studied, but they are not a comfortable escape, because feeding that violently is hard to sustain. The faster a black hole eats, the more ferociously it blazes, and the more ferociously it blazes, the harder it shoves its own food away. To keep a black hole feeding at super Eddington rates continuously for hundreds of millions of years, you need a constant torrent of gas funneled inward against the gale of its own light, and the early universe, for all its abundance, may not be able to keep that torrent flowing without interruption. Every flicker, every pause, every starburst that blows the gas away costs precious time the cosmos does not have. There is another subtlety worth naming, because it sharpens the puzzle rather than softening it. The growth clock is not just about reaching a final mass. It is about reaching it while also lighting up enough for us to see. A black hole that grew in total darkness, swallowing matter without the brilliant blazing disk, would leave no broad emission lines for us to detect. The very fact that we see these objects means they are feeding actively, pouring out light, which means they are subject to the radiation break at the precise moment we observe them. We are not catching them resting. We are catching them mid-feast, and mid-feast is exactly when the speed limit bites hardest. The universe has handed us black holes that are simultaneously too big to have grown in time and visibly straining against the very limit that should have slowed them. And layered on top of all this is the overmassive problem, which I want to press on once more because it may be the most important clue of all. In the mature universe, the black hole is a junior partner, a small fixed fraction of the surrounding mass of stars, as though some deep feedback keeps the two growing in careful proportion. The leading idea for why is that when the black hole feeds too hungrily, its blazing output heats and blows away the surrounding gas, choking off both its own food supply and the raw material the galaxy needs to make new stars. The monster regulates itself and its city together, but in the little red dots, the proportion is wildly off. The black hole is a giant, and the galaxy a relative dwarf. Either that self-regulating feedback had not yet kicked in, or these objects formed through a path where the black hole genuinely came first, and the galaxy is still racing to catch up. Both possibilities are profound. Both suggest that in the deep past, the rules we take for granted simply did not yet apply. Before we meet the suspects, sit for one more moment in the discomfort, because the discomfort is the point. Productive confusion is not the same as ignorance. Ignorance is not knowing and not caring. Productive confusion is the electric state of knowing exactly what you do not understand, of seeing the precise shape of the hole in your knowledge. The astronomers were not lost. They knew with great precision what the data said. They could measure the redshift to several decimal places. They could measure the width of the broad lines. They could calculate with well-tested methods the mass those measurements implied. Every individual step was solid. It was only when they assembled the steps into a single picture that the picture refused to make sense. That is the most valuable kind of confusion there is, the confusion of solid facts that will not fit together, because that confusion is the doorway through which every scientific revolution has ever walked. When the facts are firm and the story is broken, you do not get to keep both. Something has to bend, and whatever bends teaches you something new about the world. So that is where we stand, at the threshold of the mystery proper. We have a real, abundant population of objects from the dawn of cosmic time. We have measured their distances and trust them. We have read their light and found the fingerprint of fast-moving gas and massive hidden engines. We have a speed limit on black hole growth that says these engines should not exist yet, and a galaxy-black hole relationship that says they are too heavy for their homes. And we have two broad escape routes, each demanding that we surrender something we cherished, either our reading of the light or our story of the cosmos. This is not a problem with a known answer that I am withholding for dramatic effect. This is the live, unfinished, genuinely contested frontier, and the people working on it are arguing in real time. So let us do them the honor of taking each idea seriously. These competing explanations are not dull academic footnotes. They are a genuine detective story playing out at the edge of human understanding, with the same red dots serving as the body in the library that every theory must account for. Each suspect explains some of the clues beautifully and stumbles on others. None of them yet explains everything. And so, with the impossibility laid bare before us, let us do what any good investigator would do. Let us line up the suspects, hear each one out, and see which of them, if any, can survive contact with the evidence. Every good mystery comes down to a room full of suspects, each with a story that fits some of the facts and strains against others. The little red dots have at least 3, and as the evidence pours in, the case keeps shifting beneath everyone who tries to solve it. Let us meet them one at a time, and give each a fair hearing before we judge. Our first suspect is the most conventional, and conventional is not an insult here. In science, the ordinary explanation deserves to be tested first and discarded last. This suspect says that a little red dot is a dusty, active galactic nucleus. Let us unpack that. An active galactic nucleus is a supermassive black hole in the middle of feeding, surrounded by that blazing disk of infalling gas we described earlier, pouring out tremendous light. We see these all across the universe. They are familiar. The new ingredient is the dust. Imagine wrapping that brilliant central engine in a thick veil of cosmic grime, fine grains of carbon and silicate floating in the surrounding gas. Dust has a particular habit. It absorbs blue light greedily and lets red light slip through more easily. So a brilliant blue-white engine seen through a heavy shroud of dust would look, from the outside, deeply red. Suddenly, the redness of the dots has a natural explanation. The compactness fits too, because the central engine is genuinely tiny. And the broad emission lines fit beautifully, because a feeding black hole is exactly the kind of thing that whirls gas around at thousands of kilometers per second. For a while, this felt like the obvious answer. A little red dot is just a young, feeding black hole seen through dust, clean and tidy. But the tidy answer began to fray when astronomers looked harder. If these objects are luminous, dusty feeding black holes, they should betray themselves in other kinds of light. A black hole feeding hard enough to power that broad line should blaze in X-rays, the high-energy radiation that pours out of the superheated gas closest to the center. It should also, in many cases, show a glow in radio waves. But when astronomers searched for these telltale emissions from the little red dots, the dots were strangely silent. Far too quiet in X-rays, quiet in radio. A dusty, feeding black hole that bright should shout across the spectrum, and instead these whispered. That silence is a serious problem for the simple dusty engine story, and it sent the detectives back to the evidence board. Our second suspect throws out the black hole almost entirely. What if the little red dots are not powered by a feeding monster at all, but by an extraordinarily dense knot of stars? Picture a star cluster unlike anything in the universe today. Hundreds of thousands or millions of stars crammed into a region absurdly small, packed so tightly that the early universe could perhaps assemble such a thing where the modern universe cannot. A cluster like that would be compact, satisfying the point source appearance, crowded with young hot stars and laced with gas and dust. It could plausibly take on a reddened color. And in such a crushingly dense environment, stars would interact violently. They would pass close to one another, collide, get torn apart. Some models suggest that the chaos of such a place, the tidal disruptions and the brilliant transient flares as stars are shredded, could even mimic some of the broad and variable features we see, without any need for a supermassive black hole at the center at all. It is a clever escape, because if there is no overmassive black hole, then there is no impossible timeline to explain. The crisis evaporates. But this suspect has its own troubles. The broad emission lines in the best little red dot spectra are persistent and well-shaped, not quite the ragged flicker you might expect from a chaos of stellar collisions. And building a star cluster that dense, that early, and explaining why such clusters would be so common in the young universe and then vanish, is its own steep mountain to climb. The dense cluster idea remains in the room, a real suspect, but it has not yet produced an airtight account of everything we see. And then there is the third suspect, the one that makes physicists lean forward in their chairs, because it dissolves the boundary between two things we thought were entirely separate. The idea has been given the wonderfully blunt name black hole star. Hold the strangeness of those two words together, a black hole and a star. In this picture, a little red dot is a supermassive black hole in a furious early phase of growth, But it is not naked. It is wrapped in an enormous, dense cocoon of gas, so thick and so vast that the whole system behaves, from the outside, almost like a single colossal star with a black hole burning at its core instead of nuclear fusion. The black hole feeds and blazes deep inside, and the immense surrounding envelope of gas glows and processes that light, reshaping it before it ever escapes to us. The object is neither purely a black hole nor purely a star, but a hybrid, a thing the modern universe does not make, and the infant universe perhaps did. This is where one of the most important recent discoveries enters, and it ties directly back to the heart of the crisis, the impossible masses. Remember that the alarming black hole masses came from the width of the broad emission lines. We assumed those lines were broadened by gas physically orbiting at enormous speed, the swung stone on the gravitational string. But there is another way to broaden a line that has nothing to do with orbital speed. If light passes through an incredibly dense fog of free electrons, those electrons scatter the light, bouncing the photons around and smearing their wavelengths. This is called electron scattering, and it can broaden a spectral line even if the gas as a whole is not moving especially fast. It is a kind of optical illusion in the spectrum, a fog that fattens the line. When astronomers took the very highest quality spectra of little red dots and studied the precise shape of the broad lines, some found exactly the fingerprint of this scattering. The lines had a particular profile, a narrow intrinsic core sitting inside broad smeared wings, the signature you would expect if a fundamentally slower moving gas was being seen through a dense scattering cocoon. And the implication is enormous. If much of the line width comes from scattering rather than orbital motion, then the gas is not orbiting nearly as fast as we assumed, which means the central mass needed to hold it is far smaller than we calculated. Some of these analyses suggest the true black hole masses could be lower than the first estimates by a factor of 100 or more, dropping from hundreds of millions of solar masses down toward the range of 100,000 to a few million. Still substantial, still impressive for the early universe, but potentially within reach of the doubling clock, no longer flatly impossible. Do you see the beauty of this? It is a possible resolution that comes not from throwing away the black hole, but from realizing we may have been misreading its scales the whole time. The cocoon explains several things at once. It explains the redness, because the dense gas reprocesses and reddens the light. It explains the strange quiet in X-rays, because such a thick envelope could absorb and smother the high-energy radiation before it escapes, muffling the shout into a whisper. It explains the peculiar shape of the broad lines through scattering, and it eases the timeline crisis by shrinking the masses. The dense ionized cocoon has become one of the most compelling frames for understanding these objects, a way to keep the black hole while taming the impossibility. But, and this is the honest heart of the matter, it does not close the case. Lowering the masses helps, yet it does not by itself explain how even 100,000 solar mass black hole came to exist so early, nor why these objects appear in such numbers, nor why they fade as the universe ages. And other careful studies push back, arguing that for at least some little red dots, the evidence for a genuine accreting black hole is unambiguous, complete with the spectral signatures that only a true active nucleus can produce. The iron-rich features, the high ionization gas, the fluorescence that demands an intense flood of ultraviolet light from a central engine. These point firmly at a black hole, dense cocoon and all. The field has not collapsed into one answer. It has fractured into a vigorous, productive argument, with the same red dots glowing at the center of every rival theory. So where does the detective story stand? The dusty active galactic nucleus suspect explained the easy clues but stumbled on the silence in X-rays and radio. The dense star cluster suspect removed the impossible black hole but struggled to reproduce the clean, persistent broad lines and to justify its own existence. The black hole star and its dense ionized cocoon emerged as the suspect that ties the most threads together, reframing the masses, the color, and the silence in a single picture, while still leaving the deepest origin question open. It is the leading candidate, not the proven culprit, and the most intellectually honest astronomers will tell you plainly that the truth may turn out to be a blend, that little red dots may not all be the same kind of object, that this red, abundant population could hide more than one phenomenon wearing the same disguise. That uncertainty is not a failure of the science. It is the science, caught in the act of working. Every new spectrum, every cleverly lensed object that nature magnifies for us, every survey that adds more dots to the sample shifts the weight of evidence a little. The case is genuinely live. Theories that looked strong a year ago are being revised right now, and ideas that sounded outlandish are gathering support as the data sharpens. We are watching, in real time, the slow, careful birth of an understanding that does not yet exist in any textbook. It is worth dwelling on that strange phrase, black hole star, because it captures something genuinely new about how scientists are being forced to think. For a long time, we kept two categories firmly apart in our minds. A star is an object that shines by fusing light elements into heavier ones in its core, held up against its own gravity by the outward pressure of that fusion. A black hole is the opposite kind of thing entirely. A region where gravity has won so completely that nothing escapes, no fusion, no light from within, only the brilliance of matter screaming as it falls in from outside. These felt like opposite ends of existence. The black hole star idea smears that boundary. It imagines an object where a growing black hole sits at the center, but the vast surrounding envelope of gas is so dense and so deep that it behaves like the outer layers of an enormous star, glowing and swelling and reprocessing the fierce light from the engine within before any of it reaches the outside universe. From far away, you would not see a naked black hole or an ordinary star. You would see a single puffed-up, reddened object, and you would struggle to say which of your old categories it belonged to, because the honest answer is both and neither. What makes this more than a flight of fancy is that it grew out of trying to explain the actual data rather than out of someone wanting to be exotic. The dense cocoon was not invented to be strange. It was reached for because it accounts for so many awkward observations at once: the redness, the muffled X-rays, the peculiar shape of the broad lines. That is the mark of a serious scientific idea. It is not judged by how wild it sounds, but by how much of the stubborn evidence it can quietly absorb. And when a single picture starts explaining several unrelated puzzles together, scientists lean toward it, even when it overturns a comfortable boundary they had held for a century. That is how progress usually arrives, not as a thunderclap, but as a quiet realization that the strange new frame simply fits the facts better than the familiar one. Still, I want to keep us honest about the disagreement, because the disagreement is real and it is healthy. There are careful researchers who look at the same little red dots and conclude that the dense cocoon and electron scattering are being asked to do too much work. That for a good number of these objects, the simplest reading of the spectrum is a genuine massive black hole feeding behind dust, with all the timeline trouble that implies. There are others who suspect the population is not uniform at all, that some little red dots are reddened feeding black holes, some are dense knots of stars, and some are the cocooned hybrids, all swept together under one name, simply because they look alike at a glance through our instruments. The name Little Red Dots describes an appearance, not necessarily a single physical thing, and history is full of cases where one name turned out to hide several distinct phenomena. It is entirely possible that future astronomers will look back and laugh gently at the way we lumped them all together, the way earlier observers once lumped together objects we now know to be wildly different. And there is a deeper reason the case stays open, one that has nothing to do with cleverness and everything to do with the sheer difficulty of the observations. We are working at the absolute limit of what even the most powerful telescope ever built can do. The light is faint. The objects are tiny. The signatures we argue over live in the subtle shapes of spectral lines that take heroic effort to measure at all. At this frontier, small differences in how you analyze the data can lead to different conclusions, and that is not a scandal. It is simply what the edge of the possible looks like. The dust has not settled because the dust cannot settle until the data sharpen further, and the data sharpen one painstaking observation at a time. Anyone who tells you they are certain what the little red dots are is telling you more about their confidence than about the evidence. There is one more thing I want to highlight about how this investigation actually proceeds, because it reveals something lovely about how science narrows in on the truth. Notice that no single observation has settled the case. Instead, each different kind of measurement rules out a little more of the possibility space. The silence in X-rays wounded the simple, dusty engine idea. The clean, persistent shape of the broad lines strained the chaotic star cluster idea. The narrow core inside the broad wings pointed towards scattering and the cocoon. The iron-rich features and the high ionization gas and the fluorescence pointed firmly back toward a real central engine. Each clue closes a door or opens one. The suspects are not judged by argument alone, but by their ability to survive a gauntlet of independent tests, and a good theory is one that keeps surviving as the tests multiply. This is the slow triangulation of truth, the way many imperfect measurements, none decisive on its own, gradually converge to corner reality. We are watching that triangulation happen in real time, and the corner is tightening, even if the culprit has not yet been named beyond doubt. And notice too how the leading idea, the dense cocoon, earns its place precisely by being the most economical. A weaker theory needs a separate excuse for every awkward fact. Why so red? A special reason. Why so quiet in X-rays? Another special reason. Why the odd line shape? Yet another. The cocoon, by contrast, reaches for a single physical situation, a black hole buried in a thick shroud of dense ionized gas, and from that one situation the redness, the muffled X-rays, and the strange line profile all tumble out together as natural consequences. Scientists are drawn to that kind of explanation not because it is comforting, but because nature, again and again across the history of physics, has rewarded the search for the single cause behind the many symptoms. When one simple picture quietly resolves a pile of separate puzzles, it has earned the right to be taken seriously, even when it asks us to blur a boundary we thought was permanent. And yet, the very fact that the leading idea requires us to invent a kind of object the modern universe does not make should keep us humble. We are not choosing between familiar options. We are being pushed by the weight of the evidence towards something genuinely without precedent, and the responsible response to that is neither to dismiss it nor to embrace it too quickly, but to keep gathering light and let the dots themselves decide. But step back from the suspects for a moment, because all of this debate, fascinating as it is really in service of a much larger question. Whatever the little red dots turn out to be, they are telling us something we did not know about how the very first giants of the cosmos came to be, how the seeds of supermassive black holes were planted, and how galaxies and their central monsters first began to grow together in the dark. That deeper question, the question of cosmic origins itself, is where these tiny red points lead us next. Whatever the little red dots are, they have forced a question that astronomy has circled nervously for a long time, a question that sounds simple and turns out to be one of the hardest in all of cosmology. Where do supermassive black holes come from in the first place? Not how they grow once they exist, but how they begin. What is the seed? To feel the weight of this, return to the idea of growth from a small beginning. We talked about the doubling clock, the patient exponential climb from a modest seed to a giant. The whole timeline crisis rests on the assumption that black holes start small and grow up. So everything depends on how small that first seed really was and how early it was planted. Astronomers have long debated two broad answers, and the little red dots have thrown fresh fuel on that debate. The two answers are usually called light seeds and heavy seeds, and the difference between them is the difference between a head start and a standing start in the race against cosmic time. The light seed idea is the classic one. In the very early universe, the first generation of stars formed from pure hydrogen and helium, unpolluted by the heavier elements that later stars contain. With no heavy elements to cool and fragment the gas, these first stars could grow enormous, far larger than typical stars today, perhaps hundreds of times the mass of the Sunday. Such giants live fast and die young, and when they collapse, they leave behind black holes of perhaps 100 or a few hundred solar masses. These are the light seeds. They are appealing because they form naturally and early, almost as a side effect of the first starlight. But they are small, and a small seed, even feeding at the Eddington limit without pause, faces that brutal arithmetic of needing many doublings, more time than the early universe seems willing to grant, to reach the masses we appear to see. The light seed runs the race, but it starts far back from the line and the clock is merciless. The heavy seed idea is bolder, and the little red dots have made it suddenly fashionable. What if some black holes skipped the star stage entirely? Imagine a vast cloud of gas in the early universe that, under the right conditions, does not fragment into many ordinary stars, but instead collapses more or less directly as a single coherent body, funneling an enormous amount of mass straight down into one place. This process, sometimes described as direct collapse, could in principle produce a seed black hole of 10,000, 100,000, even a million solar masses right from the start. No long stellar prelude, no waiting. A heavy seed begins the race already most of the way to the finish line. If nature can plant seeds that large that early, then the supermassive black holes of the infant universe stop being impossible and start being almost expected. The conditions required for direct collapse are demanding and specific, and astronomers argue about how often the early universe could really achieve them. But the little red dots, with their hints of large black holes in tiny young galaxies, look tantalizingly like the kind of thing a population of heavy seeds might produce. They may be heavy seeds caught in the act of their first growth, the earliest activity of black hole formation made visible. And this connects to that astonishing word from earlier, overmassive. Remember the tight partnership we see in the modern universe between a galaxy and its central black hole, the fixed ratio that suggests they grew up together as equals. If the little red dots are showing us black holes that are far too heavy for their small host galaxies, then they may be capturing a moment before that partnership settled into balance, a moment when the black hole led and the galaxy had not yet caught up. This would rewrite the order of creation. Instead of galaxies forming first and slowly growing black holes in their hearts, perhaps in some places the black hole seed came first, a heavy anchor planted early, with the galaxy of stars accumulating around it afterward. The monster in this telling is not the product of the city. The city grows up around the monster. If that is true, it changes how we understand the architecture of the entire cosmos. The supermassive black holes sitting at the centers of galaxies today, including the one at the heart of our own Milky Way, would trace their lineage back to these early heavy seeds, these first furious episodes of growth that the little red dots may be revealing. Every great galaxy would carry, at its core, the descendant of something that switched on in the first few 100 million years of time, in an age the little red dots let us glimpse for the first time. We would be looking, in these tiny crimson points, at the founding events of cosmic structure. But I want to be careful and honest here, because this is the frontier, and the frontier is humbling. We do not know that the little red dots are heavy seeds. We do not even fully agree on whether their black holes are as massive as they first appeared, given the cocoon and the scattering that may be inflating our measurements. What the little red dots have truly done is expose how much our confident story was hiding. They are a stress test that our models are partly failing. And there is a particular kind of intellectual humility that this moment demands. The humility of realizing that a population this large was sitting in the early universe all along, that it shaped the dawn of cosmic time, and that our best theories did not predict it, and our best telescope had to stumble into it before we even knew to look. This is worth dwelling on, because it says something profound about the nature of knowledge itself. The patient story of slow cosmic growth was not foolish. It was built on real evidence, refined by brilliant people, and confirmed again and again within the range of what we could see. Its mistake, if you can even call it that, was the quiet assumption that the part of the universe we could see was representative of the part we could not. The little red dots lived in a region of cosmic time that our instruments could barely reach, and so they stayed invisible, and so our story stayed comfortable. The lesson is not that scientists were careless. The lesson is that the universe is under no obligation to confine its strangeness to the places we have already looked. There is always a deeper field, always a fainter signal, always a redder dot waiting just beyond the edge of the current map. And the hunt is far from over. This is one of the most thrilling parts of the present moment. The little red dots are not a closed chapter being written into history. They are an open investigation, and the tools of that investigation are growing sharper by the month. Astronomers are using a beautiful trick that nature provides for free, called gravitational lensing, where the gravity of a massive foreground galaxy cluster bends and magnifies the light of objects behind it, acting as a giant natural lens. Through these cosmic magnifying glasses, faint little red dots that would otherwise be too dim to study in detail are stretched and brightened, letting astronomers read their spectra with a clarity that would otherwise be impossible. Some of the strongest evidence in the whole debate has come from these lucky lensed objects where nature itself leaned in close so that we could see. At the same time, deep spectroscopic surveys are systematically gathering more and more of these objects, building the sample from a handful of curiosities into a proper statistical population, because patterns that hide in one object reveal themselves in 100. Astronomers are searching for how the dots change over time, watching for the flickers and variations that could distinguish a feeding black hole from a dense cluster of stars. They are hunting at ever higher redshifts, pushing toward the most distant little red dots yet found, each one a step closer to the very first moment such objects could exist. And they are catching a few of these dots in apparent transition. Objects that seem to be evolving toward the bright quasars of slightly later cosmic time, hinting that the little red dots may be an early phase. A chrysalis stage in the life story of the supermassive black holes that would later blaze across the universe. Every one of these efforts is a thread being pulled, and the remarkable thing is that the picture genuinely shifts as they pull. A few years ago, the little red dots barely had a name. Now they sit at the center of one of the liveliest debates in astrophysics, with rival camps marshalling evidence, with new spectra arriving that overturn last season's consensus, with theorists racing to build models that can accommodate an abundant population of early, overmassive or cocooned black holes. We are living through the unsettled middle of a scientific story, the part that never makes it into the tidy textbook summary, the part where nobody yet knows how it ends. And that, I think, is the real gift of the little red dots, beyond any single answer they may eventually yield. They are a reminder that the universe at large scale, the cosmos of the deep past and the deep dark, is not a solved and finished thing sitting quietly in our archives. It is a living question. The dawn of cosmic time, the era when the first light broke, the long darkness and the first giants began to grow, is not fully understood. It is being actively rewritten right now by faint red light caught in a golden mirror beyond the moon. We thought we knew how the universe built its monsters. The little red dots have told us, gently and undeniably, that we were missing something enormous hiding in the oldest light there is. Let me draw out one more thread from the seed question, because it connects to something close to home, closer than 13 billion years might suggest. Our own galaxy, the Milky Way, harbors a supermassive black hole at its center, a giant of some 4 million times the mass of the Sunday. For a long time, it was just a number in a textbook, an abstract monster in the galactic core. But if the little red dots are showing us the earliest growth of black holes like it, then the story of that central giant reaches all the way back to the era these crimson points illuminate. The black hole at the heart of our galaxy had a beginning. It was once a seed, and whether that seed was a light one left by a dying first star, or a heavy one born from a directly collapsing cloud, is not a distant abstraction. It is the origin story of the gravitational anchor around which our entire galaxy, and by extension the conditions that allowed our sun and our world to form, eventually arranged themselves. The little red dots are not someone else's history. They are a chapter of our own, written in the oldest ink there is. This is what I find quietly thrilling about the seed problem. It is not merely a technical question about black hole formation. It is a question about beginnings, about the first decisive events that set the architecture of everything that followed. If heavy seeds were common in the early universe, then the cosmos had a way of planting massive anchors early and often, and the grand structure we see today, galaxies marshaled around their central giants, was in some sense seeded in those first few 100 million years. If instead light seeds dominated and somehow grew with impossible speed, then the early universe must have had engines of growth we do not yet understand, ways of feeding black holes that defy our tidy limits. Either answer rewrites the opening chapter of cosmic history, and the little red dots, whatever they finally prove to be, are the first clear evidence that the opening chapter we wrote was wrong, or at the very least dramatically incomplete. I keep returning to that word, incomplete, because it is more hopeful than it sounds. An incomplete story is not a broken one. It is an unfinished one, and unfinished means there is still work to do, still wonder to be had, still room for discovery. There is a temptation, when we hear that scientists were surprised, to feel that science failed, that the experts did not know what they were talking about. But that gets it exactly backward. The fact that we can be surprised at all is the triumph. It means we built instruments precise enough and theories sharp enough that reality could push back against us in a clear and measurable way. A vague theory can never be surprised because it predicts nothing in particular. Only a strong, specific, confident theory can be caught out by the universe. And being caught out is how strong theories become stronger ones. The little red dots are not an embarrassment to cosmology. They are cosmology working precisely as it should, bumping hard against something it did not expect and turning eagerly to investigate. And investigate it does, with a vigor that is genuinely inspiring to watch. Think of the global effort wrapped around these tiny objects. There are observers planning which faint targets to point the telescope at next, fighting for precious hours of observing time. There are instrument specialists wringing every last photon of sensitivity out of the detectors. There are theorists at their whiteboards, building models of cocoons and seeds and feedback, testing each against the spectra as they arrive. There are the great simulations being rerun with new physics added, trying to grow a digital early universe that finally produces little red dots in the right numbers. It is a vast, distributed, collaborative act of human attention. Thousands of minds across the world all turn toward the same faint red specks at the edge of time, all asking the same patient question. What are you? And what are you trying to tell us about how everything began? There is a further implication here that deserves to be spoken plainly, because it reaches beyond black holes into the whole shape of cosmic history. If black holes were already massive and abundant in the first few 100 million years, then they were not bystanders in the building of the universe. They were participants from the very start. The energy a feeding black hole pours into its surroundings can heat gas, drive winds, and reshape the growth of the galaxy around it. A universe that switches on massive black holes early is a universe where those black holes help write the story of how galaxies themselves take shape. The little red dots in this light are not just curiosities about black hole formation. They are a clue that the early cosmos was a more active, more interconnected, more dramatic place than the gentle picture allowed, with giant engines and growing galaxies shaping one another from the opening scene rather than settling into partnership only much later. This is why so many different fields of astronomy are leaning in at once. The people who study black holes care, because the seed problem is theirs. The people who study galaxy formation care, because the overmassive ratio breaks their cherished relationship. The people who study the early universe and the first light care, because these objects are among the earliest detailed sources we can examine. The people who build cosmological simulations care, because their digital universes need to reproduce this population or be revised. A single class of faint red specks has reached into nearly every corner of the field and asked each of them a hard question. That is the mark of a truly important discovery. It does not stay politely in its own lane. It sends ripples through everything, forcing connections between questions that once seemed separate, reminding us that the universe is not divided into the neat subjects we invented for our textbooks, but is one continuous, interwoven whole. And we should be honest that the answers, when they come, may be stranger than any of the current suspects. The history of astronomy is full of moments when the truth turned out to be none of the options on the table, when the real explanation required a concept nobody had yet thought to propose. It is entirely possible that the full account of the little red dots will involve physics we are only beginning to glimpse, or a combination of effects no single team is currently championing. That possibility should not frustrate us, it should delight us. It means the universe still has room to teach us things we cannot yet imagine, that the frontier is not a thin line we are about to cross, but a wide country we have barely entered. The astronomers chasing this mystery today may well be remembered the way we now remember the first people who realized those faint smudges in the sky were other galaxies. They are mapping the edge of the known, and the edge of the known is exactly where the next revolution always begins. So as we turn toward the close of this journey, let us carry that feeling with us, the productive vertigo of a settled story coming unsettled. Because the deepest meaning of these tiny crimson points is not really about black holes or seeds or cocoons at all. It is about what it means to be a small, curious creature, looking up and discovering that the oldest light in existence still has secrets. It has not finished telling. There is something quietly staggering in the simplest fact of this whole story, and I want to end by holding it up to the light. The little red dots were always there. For more than 13 billion years their light had been traveling toward us, falling through the swelling dark, patient and unhurried, carrying a message from the infancy of everything. It crossed an unimaginable gulf. It outlasted the birth of the sun and the earth and every living thing that has ever drawn breath. And it arrived, finally, at a moment when there happened to be a creature ready to catch it and ask what it meant. The light did not wait for us. We simply learned, at last, how to listen. Think about what that means. The universe hid an entire, abundant population of objects in plain sight, woven into the oldest light there is, and our finest theories never saw them coming. Not because the theories were stupid, but because the cosmos is larger and stranger than the part of it we had managed to examine. For a century we told ourselves a story of patient, slow growth, of monsters built ring by ring across the ages, and the story was beautiful and mostly right and quietly incomplete. It took a new eye, unfolded in the cold beyond the moon, looking back toward the dawn, to reveal the gap. The little red dots are the shape of our own ignorance made visible, and there is a strange comfort in that. It means the great questions are not all behind us. The frontier is still open. The map still has edges, and beyond those edges, more. Here is what I find most moving. We still do not know what the little red dots truly are. We have suspects. We have a leading idea: the dense ionized cocoon, the black hole wrapped in glowing gas, masquerading from the outside almost like a single colossal star. We have rivals: the dusty feeding nucleus, the impossibly dense cluster of stars. We have a measurement crisis that may be partly an illusion of scattered light, and black hole masses that may shrink under closer inspection but will not vanish. We have a seed problem that reaches back to the very first stars and the very first collapsing clouds. And we have, threaded through all of it, the astonishing possibility that in some corners of the early universe, the black hole came first, and the galaxy grew up around it, reversing the order of creation we had assumed. We do not get to close the book tonight, and that is exactly as it should be, because a question still alive is worth more than an answer prematurely sealed. The little red dots are not a fact to be memorized. They are an invitation. They are the universe leaning down and whispering that it is not finished surprising us, that the dawn of cosmic time is still being read, line by faint red line, by people alive in this very moment, with instruments still warming to their task. Some of the children who will finally untangle this mystery are alive right now. Perhaps one of them is watching this. Perhaps one of them is you. Let me sit with you for a while in that not knowing, because our culture treats not knowing as a kind of failure, and I think that is one of the saddest mistakes we make. We are taught from childhood to chase the right answer, to fill in the blank, to close the question and move on. And there is a place for that. But the deepest joys of being a conscious creature in a vast universe do not come from the answers we have closed. They come from the questions we are still living inside. A solved mystery is a beautiful thing to own. An unsolved one is a beautiful thing to inhabit. The little red dots are an invitation to inhabit a question larger than yourself, to stand at the edge of human knowledge and feel the wind coming off the dark water of everything we have not yet learned. And what a question it is. Consider once more what these objects actually represent. In the first few 100 million years after the beginning of time, in an era so early that the universe had barely cooled from its fiery birth, something was already building giants. Whether they are overmassive black holes feeding behind dust, or black holes shrouded in glowing cocoons of gas, or some hybrid we do not yet have the right words for, the plain fact remains. The dawn of cosmic time was not the gentle, slow place we imagined. It was already doing something powerful and strange, something our models did not anticipate, something that left the same crimson signature across the early sky again and again. The universe was busy in its infancy. It was making monsters while it was still a child, and it did this everywhere, abundantly, as a matter of routine in a way that we are only now, with our newest eye, beginning to perceive. There is a humbling symmetry in how this discovery came about. We built the most ambitious telescope in history, sent it to a frozen perch 1,000,000 miles away, unfolded its golden mirror and its great shield with a sequence of maneuvers so delicate that any single failure would have doomed the mission. All of it carried out flawlessly in the dark, where no human hand could reach to fix a mistake. We did this to confirm and refine our understanding of the early universe. And the first great thing the telescope did was to show us how much of that understanding was incomplete. We reached out to verify our story, and the universe answered by complicating it. There is something almost tender in that exchange, something that should keep us forever modest. The cosmos does not exist to confirm our expectations. It exists, and we are lucky beyond measure to be the kind of creatures who can look at it and be surprised. Think about how rare that is on the scale of all the matter in the universe. Almost all of it is unconscious. Rock and gas and plasma and dark unseen stuff, vast and ancient and utterly unaware. And then, on at least one small wet world, the atoms arranged themselves into beings who could look up, who could wonder, who could build instruments to catch light from the dawn of time and argue about what it means over coffee and across continents. The little red dots have been shining at us for 13 billion years, indifferent, patient, unaware that they were sending anything at all. It took a particular and improbable kind of matter, the kind that became us, to notice. When you study the early universe, you are matter contemplating its own deepest origins. You are the cosmos, after billions of years, finally turning around to look at where it came from. That is not a small thing. That may be one of the most extraordinary things that exists. And here is the part I find almost unbearably beautiful. The light that carries this mystery is not locked away in some distant laboratory or reserved for a handful of specialists. A version of it is falling on every one of us, all the time. The same expanding universe that stretched the light of the little red dots into the infrared also fills the entire sky with the faint afterglow of the beginning itself, a whisper of radiation left over from when the cosmos first cleared and let light run free. It is everywhere. It passes through your body without your noticing. The story of the early universe is not somewhere else. It is woven into the very space you occupy at this moment, into the air of the room around you, into the dark behind your closed eyes. We do not have to travel to the dawn of time. We are bathing in its remnants right now. I think this is why these discoveries move people who have no training in astrophysics at all, people who could not write down a single equation, people who simply feel something stir when they hear that the universe is older and stranger than we knew. It is because the story is not really about black holes or redshifts or telescopes, though it lives in all of those things. It is about belonging to something vast. It is about the quiet astonishment of being a brief, warm, conscious flicker inside a cosmos that has been unfolding for billions of years and is still, even now, full of secrets it has not finished telling. The little red dots remind us that we live in an unfinished universe, in an unfinished story, and that we have arrived in time to witness a few of its surprises. That is a privilege so large it is easy to forget we are holding it. And the surprises are not slowing down. If anything, they are accelerating, because every new instrument widens the window. The little red dots were essentially invisible to us only a few short years ago. They sat in the early universe the entire time, abundant and waiting, and we walked right past them because we could not yet see in the right kind of light. What else is out there? Just beyond the edge of our current sight, waiting for the next instrument, the next idea, the next curious generation to finally perceive it. The honest answer is that we do not know, and that not knowing is the most exciting sentence in all of science. There are little red dots in every field of human inquiry, faint anomalies sitting quietly in the data, waiting for someone with the right eyes and the willingness to lean in rather than look away. The universe has not run out of ways to astonish us. It has barely begun. So I do not want to leave you with an answer tonight, because I do not have one, and because an answer would be a smaller gift than the truth. The truth is that the dawn of cosmic time hid a population of impossible objects in its oldest light, that our finest theories missed them, that our newest eye found them, and that we are right now, in this very year, living through the unsettled, thrilling, unfinished work of figuring out what they are. You are alive at a moment when one of the great questions of cosmic origins is wide open. Most people who have ever lived died without ever knowing such a question existed. You get to know it. You get to carry it with you. You get to wonder. Let me offer you one image to carry, because images last longer than arguments. Picture a single photon, a single particle of light, leaving the glowing edge of a little red dot when the universe was a few 100 million years old. At that moment, there is no Earth. There is no Sunday. The atoms that will one day become your body are scattered across clouds of gas that have not yet collapsed into stars. And that photon sets out across the dark, falling through expanding space, stretching slowly from blue toward red as the eons pass. It travels while the first generations of stars live and die. It travels while our galaxy assembles. It travels while the sun ignites and the planets form and the earth cools and the oceans gather. It travels while life begins, while creatures crawl from the water, while forests rise and fall, while the first humans look up and invent stories about the lights in the sky. It travels through all of recorded history, through every empire and every song, indifferent, patient, unhurried. And then, after more than 13 billion years, on a particular night, that single photon ends its journey in the cold mirror of a telescope we built and flung into the dark, and becomes one faint speck of data that helps a curious species understand its own origins. That is not a metaphor. That is literally what happened billions upon billions of times to make the discovery we have been discussing. When you understand that, the night sky changes. It stops being a flat, black ceiling sprinkled with decoration and becomes what it truly is, a deep well of time, a vast archive of light arriving from every era of cosmic history at once. The nearest stars send you light a few years old. More distant ones send you light older than human civilization. And the faintest reaches, the little red dots and their kin, send you light nearly as old as time itself. To look up is to look down a tunnel into the past. All the ages of the universe stacked one behind another, all of them present in the same patch of sky, all of them falling on you in the same quiet instant. We are, every one of us, sitting at the receiving end of the longest journeys that exist. And there is a gentleness in this that I want you to feel, especially as the day winds down. The universe is enormous and old and full of forces that dwarf us beyond comprehension. It would be easy to find that frightening, to feel small and lost against such a backdrop. But I think the truer feeling is something closer to belonging. We are made of material forged inside stars. We are kept alive by light from a star, and we have learned, against all odds, to read the light of the most distant and ancient objects in creation, and to ask what they mean. We are not separate from this vast story. We are a part of it that has woken up and begun to pay attention. The little red dots did not have to be discovered by anyone. The universe could have gone on forever without a single mind to notice them. And yet here we are, noticing, wondering, leaning in. That is not smallness. That is one of the most remarkable things the cosmos has managed to do with itself. And the wondering does not require a telescope or a degree. It requires only that you keep your sense of awe alive, that you let the strangeness of existence stay strange, that you resist the dull habit of treating the sky as ordinary. The same curiosity that drives a great astronomer is available to anyone willing to look up and ask a real question. You already have everything you need to be part of this. You have a mind that can wonder, and a universe generous enough to keep giving it something to wonder about. And tonight, it has given you this, a population of impossible giants glowing at the edge of time, waiting in the oldest light there is for the next person willing to look up and ask what they are. So let me leave you where every one of these stories should end, with your own two eyes and the sky above them. Tonight, when the day has folded itself away and the dark comes on, step outside if you can, or simply imagine it. Look up. The points of light you see are mostly nearby, in cosmic terms, the familiar stars of our own galaxy, close companions in the dark. But the darkness between them is not empty. It is full. It is brimming with light, too faint and too far for the naked eye. Light that has been traveling since before the Earth was born. Light from galaxies and from those tiny crimson dots glowing at the edge of time. That light is falling on you right now. It is passing through the air, brushing against your skin, gathering unseen in your eyes. You are standing in a gentle rain of the oldest light in existence, and almost all of it slips by unnoticed. That is what a telescope really is. It is not a way of leaving the Earth. It is a way of finally noticing what was always arriving. And what is arriving, we now know, includes a message we did not expect and do not fully understand. A message that says the early universe built giants faster and earlier and more strangely than we ever imagined, and that it scattered them across the dawn in numbers we are only beginning to count. There is a particular kind of peace in carrying an unanswered question into sleep. Not the anxious peace of a problem you must solve, but the deep, restful wonder of a problem far larger than yourself. One that will outlast the night and be waiting, unhurried, in the morning. The little red dots have waited 13 billion years to be seen. They can wait a while longer to be understood. And there is something steadying in joining your small attention to a mystery that vast, in letting your mind rest for a moment against the gentle enormity of cosmic time. So, as you settle into the quiet tonight, Let this be the last thought you carry down into the dark. The universe is older and stranger and more generous with its secrets than we knew. It hid impossible giants in its oldest light, and then, when we were finally ready, it let us find them. We do not have the ending yet. We have something better. We have the open question, glowing faint and red at the very edge of time, patient as the dark, waiting for the next curious mind to look up and lean in. Sleep well. The oldest light in the universe will still be falling when you wake, and the dawn of time will still be there, holding its little red secrets, ready whenever you are to wonder again.